So let's start at number 1. So which of the diagrams below gives a domain for the function? And our function is log of 9 minus x squared minus y squared minus square root of 1 plus xy. Now, what's sort of a key word in this problem that you're like, I see this particular word? The domain. So when you see the domain, you're like, okay, where are my problems? There are 3 types of problems you might worry about. What are your 3 problems? Yeah. Logs are problems, square roots are problems, division are problems. So we make sure you take log, it has to be positive. Square root, it has to be non-negative, greater than or equal to 0, and no divide by 0. And essentially, if you see a domain, you say, okay, I'm just looking for these issues. All right, so that's our problem. And we see, okay, so we have a 9 minus x squared minus y squared. We see a 1 plus xy. We avoid them. Our choices A, B, C, D, or E. Answer? E. All right, so what happens? Well, of course, we said we have to worry about the log, so the inside has to be positive, which is the same as saying x squared plus y squared is less than 9. That's a strict inequality. So we have to be inside a circle of radius 3. The square root, 1 plus xy is greater than or equal to 0. That says xy is greater than or equal to minus 1. So plot y equals minus 1 over x, and pick a point. You find out that it's this band, and then you overlap, and the result is E. All right, so that's number 1. Any questions? Good.
How do you determine whether it's dotted or like?
How do you determine dotted versus solid? The answer is you look at your inequality. If it's a strict inequality, like a less than or a greater than, dotted, so you don't include. If it's greater than or equal or less than or equal to, that means you do include solid. So look at the kind of inequality. That tells you dotted or solid. Now, this is not the only kind of picture problem you may have, but you may have a picture problem. So be ready to be able to say, I know how to handle pictures. All right. That brings us to number 2. What is a unit vector for the direction of the rate of greatest decrease for the function f of xy equals x squared y plus e to the 4x minus 4 minus 7y at the point xy equals 1, 2. Okay, so again, we look for clues. Is there anything about this problem that's acting as a clue about what we should be doing or what we're being tested on? Well, certainly gradient, but what about the gradient? What suggests yeah, greatest decrease, that's code. This is saying, we are testing you on do you understand the gradient, properties of the gradient. So let's remind ourselves of some properties of gradient. If I want greatest increase, where do I look? Well, the magnitude is the value, and the direction would be just the vector. If we want greatest decrease, then what happens? Essentially negative. The negative of the magnitude is the value. The direction is negative the gradient. Now there is another word to pay attention to, and that's this word, unit. It's not just a vector, it's a unit vector. Unit vector means what? Yeah, so it means length 1. We get to a unit vector by dividing by the magnitude. So if you see a unit vector, you can rule out anything that's not a unit vector, but I'm not that nice. These are all unit vectors, but just make sure. Just make sure. All right, so we have a plan. Find the gradient. Take the negative of it, make it a unit vector. So what's the answer? A, B, C, D, or E? The answer is D. So if we take the gradient, and the gradient, as a reminder, just says collect your partial derivatives. So partial derivative with respect to x, partial derivative with respect to y. Evaluate at your point, you get the vector 8, negative 6. But we need greatest decrease, so we throw a negative there, which makes it negative 8, 6. It's not a unit vector, but now everything else is right. It's pointing in the right direction. Okay, so take the magnitude, and now scale 1 over the magnitude times the vector, which gives us 1/5 times the vector negative 4, 3. So our answer is D. Any questions on this one? All right. Well, that takes us to number 3. So this one would probably not normally be a multiple choice, but it's on the practice, so it's okay. We can throw crazy stuff into the multiple choice on the practice. Given z cubed plus 3z equals x squared plus xy plus 2y squared, then we're asked to find the second derivative of z with respect to x and with respect to y. So it's the mixed partial derivatives evaluated at the point 1, 1, 1. So there's no functions, we just have numbers coming out. And then it lists some options for us. Negative 1/2, negative 1/4, 0, 1/4, and 1/2. All right, so what's the tool here? Implicit differentiation. Now, this one was very subtle. Usually, how do you know if a problem says implicit differentiation? You look for it implicitly defined. But this one was more subtle. What about this says implicit differentiation? Well, it's hard to solve for z, right? So if you can't solve for z, then that says I don't know what z is explicitly, but I still have a relationship. Now the key for implicit differentiation is we look at it and we say, I may not know what it is, but I can pretend like I know. So we're going to think of z as being a function of x and y. And now that we have that in mind, we say, all right, what's our plan? Well, so what is the plan? What should we do? Yeah, we'll take the derivative with respect to x. And that'll be something, and we'll look at it in a second. And then what do we do after that? We'll take the derivative of that with respect to y. And then that'll be something, and then we can plug in. But here's where it gets fun. That sounds easy. But that turns out to be not enough. You also have to take the derivative with respect to y, and you'll have to plug in here, and you'll have to plug in here, as that will feed in to there. So let's see what the answer, what is the answer? A, B, C, D, or E? B. Negative 1/4. All right. So, take the derivative with respect to x. When you see the derivative with respect to x, you have to know what your mindset is. So it's like, okay, what are my variables? We're thinking of z as a function of x and y. So you have three options, x, y, and z. When we're taking the derivative with respect to x, is x a variable or not a variable? It's a variable. Is y a variable or not a variable? Not a variable. What about z? It is something that's varying, because z depends on x. So make sure you say, all right, when I take derivatives with respect to y, for example, that's going to be 0. But when I take derivatives with respect to z, I have to pull out the chain rule. So the derivative of z cubed would be 3z squared times the derivative of z with respect to x, which we write as the derivative of z with respect to x. So we find that the derivative with respect to x, we can plug in and find out that at that point, the derivative of z with respect to x is 1/2. All right. Well, let's also do the derivative with respect to y. Very similar. Plug in. Derivative of z with respect to y, 5 over 6. Now, you pick one. Doesn't matter. So here I pick the derivative with respect to y. Just take the opposite derivative. Take the derivative with respect to x. And be careful. So 3z squared partial z partial y. When we're taking the derivative of that term, what rule needs to be used? Product rule. So it's the derivative of the first, that's your 6z partial x, times the second, and then it's plus the first times the derivative of the second. And here's where your mixed partial derivatives come in. So you have to be careful here. It is not the case that partial squared z, partial x, partial y, does not equal partial z, partial x, partial z, partial y. It's tempting, it's very tempting, but it's not true. So you will lose points. Anyways, you just now plug in everything that you know, because you know partial z, partial x, you know partial z, partial y. The only thing you really don't know is what you're looking for, and then you solve, you get negative 1/4. 5 points. Haha. Don't worry. The multiple choice on the exam are definitely not as hard as this one. And they're not harder. I won't make you that nervous. I want to make you a little bit nervous. I don't want to make sure you study, but I don't want to make you too nervous. All right, any questions on implicit differentiation? Okay, so if you see an implicit differentiation, know how to be ready. Basically, make sure you understand your mindset. Now, here we have z as a function of x and y. Does it have to be z as a function of x and y? No. We could do what? Y is a function of x and z. We could do all sorts of stuff. Yes?
So you should just like keep z on the x side and then like differentiate implicitly instead of like moving it over so that there's a 0 on one side?
So when we're doing implicit differentiation, we don't have to have all the variables on one side. You can if you want. Now, there are cases where you do want all the variables on one side, and we will run into that. But in implicit differentiation, the moral is take the derivative of both sides. So you don't have to move all the variables over. You can if you want to. You won't lose any points, and if it helps you, do it. Anything else? Yes?
You have two values for both partial z partial x and partial z partial y. How do you know which one you're using?
What do you mean, how do I know which one I'm using? So this is where notation comes in. So you can't write z prime, unfortunately. This is why you can't just say, z prime. No, because it's like, well, but what's kind of derivative of z? Is there another question?
So you have partial y and then partial x. Does it matter the order? Could you have partial x and then partial y?
It won't matter the order. You'll get the same answer. So yeah. So the order. Now, will it ever be the case that sometimes taking a derivative one way is slightly easier than the other? Sometimes, but it's so marginal that it's not worth stressing about. Now, I will tell you there's something I do that usually the book says not to do. Or the book says, if I were the book would say, hey, solve for partial z partial x at this point. But do you know what that means? Fractions. I don't like fractions because then you get into quotient rules, and then I gotta remember, is it low d high or is it high d low, and and so I try to avoid fractions. So if you want to solve, you can, and then take a derivative, but that introduces its own kind of headaches. So there's other ways to go about doing this. And contrary to popular belief, we do understand there are other ways of solving problems, and we do give credit for them. If it's a really exotic way to solve a problem, you may have to come talk to us, but we'll still give you the credit. All right. Number 4. Use linear approximation of our function, the square root of x squared plus y cubed plus 1, at the point xy equals 4, 2, to estimate g of 4.1, 2.05. All right, well, we look at this. There's a word that jumps out to me, linear approximation. When we see linear approximation, what does that tell us? What is linear approximation? Not gradient. Taylor polynomials, kind of, but more simply, it's tangent plane. So when you see linear approximation, it's like, oh, you're asking me to find the tangent plane, because that's what it is. Now, it is true it's a Taylor polynomial. It's a Taylor polynomial of order 1. But somehow that makes things more sort of scary when I say Taylor polynomials. I think too many people remember Calc 2. And so linear approximation just says I'm trying to approximate by a flat thing. Our favorite flat thing in multivariable calculus is a plane. Okay, so if you see linear approximation, think tangent plane. And so in general, what's your function? Well, g of xy will be approximately the value of the function plus you take the derivative with respect to your first variable. It doesn't have to be x, it often is, times x minus a, derivative with respect to your second variable, y minus b. So this is your linear approximation, also your tangent plane. And it's a good approximation nearby, so the idea is plug in your points, and there you go. A couple of things to be careful of. This would never happen to you, but I'm just going to say it. What do these three things have in common? They're numbers. So make sure you evaluate them. Your linear approximation should look like a plane because it's a plane. All right, so our answers, A, B, C, D, or E, what does it turn out to be? D. Okay, so for us, we have our linear approximation, and so we take our appropriate derivatives, we evaluate. The g sub x is 8/10, g sub y is 12/10. You can simplify if you want to. So this is our generic linear approximation. You plug it in, and then you just patiently clean it up. So you get 5.14. All right. So, all right, that's not too bad. This could be reasonable for the exam. Any questions on this one? Okay. Well, that brings us to number 5. Find the tangent plane to the implicit surface x squared z plus 3y cubed equals x cubed plus 2yz squared plus 1 at the point xyz is 1, 1, 1. Okay. So, tangent plane to an implicit surface. Now, an implicit means you can't solve for z in a nice way. You could solve for z in a not nice way using the quadratic formula, but we wouldn't want to do that because that sounds not nice. So, what do we do? What's our game plan? Gradients, right. So the idea is there's two ways to do tangent planes. One is the one we just talked about, which is the linear approximation way. The second way is to say, I have a surface which is secretly a level surface for some high dimensional function. So we're thinking gradients. Are we ready to take gradients? And why not? What?
Not on the same side.
What's not on the same side?
All the variables are on things either side of
Yeah, so you have to be careful. If you want to do the gradient, which is probably the ideal way to take tangent planes, you have to be in the form f of x, y, z equals to some constant k. But we have variables on both sides, so no worries. Just move stuff around. I mean, equal signs, you just subtract stuff over, and life is good. So that's our f of x, y, z. All right, now, why do we take the gradient? What does the gradient give us? Well, the point is given. The gradient gives us what? Vector, and particularly the normal vector. Okay, so you know how to take a normal vector and make a plane. What else can you do with this gradient vector? Besides just making a plane, what can you do? Channel maybe the first exam. Well, I made a plane, but I also can make a line. What line would it be? The normal line. It'd be the line perpendicular. So know how to make a plane, know how to make a line. Now for us, we have options A, B, C, D, or E. What does it turn out to be? Oh yeah, sure, you betcha, eh? You betcha. It's A. All right, so we moved everything over. And that's why, move all variables over to one side. We mentioned before, for implicit differentiation, you don't need to do that. But when we're using the gradient to make a normal vector, you do. So you may have said, oh, I'll just find the gradient of this function, x squared z plus 3y cubed. And then you probably said, perfect, it was one of these other options. Very tempting. All right, so we moved everything over. We took the gradient. Gradients are partial derivatives. Plug it in. And as soon as you know your gradient vector, you can read off which one has the right coefficients. You can stop. Remember, for multiple choice, you just have to know which one's right. You don't have to prove it to the end. And so if you get to a point and say, aha, I can now figure out which one of these is right, you can stop. And give yourself more time on other problems. Or if you like to, you can keep going. We like to live dangerously. It's a bold move. We'll see if it pays off. All right. So once you have your normal, that gives you your coefficients of your plane. Then you say, well, wait, that's not quite the plane. There's this little piece left. To figure that last piece, you plug in the point. So plug here 1, 1, 1. Tells you that this last piece is 3. So here's the plane. Now remember, planes are not unique. You can always scale. In this case, you scale by -1. All right, questions on this one? Yes?
Isn't that plus 3z?
Isn't it what?
Never mind.
Oh. Phew. Oh, I was worried. All right. How you doing so far? Feeling good? 2 right. Nice. Well, of course, these are the ones that are only worth 5 points each. The important ones are coming up in a few minutes. Our last multiple choice. Find the rate of change of the function, and our function is 10y squared minus 5xy squared minus e squared, from the point 2, 1, 3 in the direction towards the point 5, 3, -3. Okay, so what kind of problem is this? How do we know? Directional derivative, correct. How do we know? What are some words that we see? Direction, and also rate of change. Rate of change means derivative, and direction means direction. So this is directional derivative. How do you do directional derivatives? Yeah, it comes from gradient. So it's the gradient of h at your point dot u. Make some notes. What is u? Yes. Be careful. It's not just an arbitrary vector. It needs to be the unit vector. Now, they might give you a vector. If they're really generous, they'll give you a unit vector. They might not give you a vector. They might give you points. So be ready to adapt to whatever situation they present you. All right, so our options are 1, 2, 3, 4, or 5. That's lovely. What's the answer? C, 3. All right, so we have our approach. We take our gradient. We take our gradient and plug in our x equals 2, y equals 1, z equals 3. So make sure you know which point you have, because here it gave you 2 points. So you have to say, aha, I know I'm at that point. That's the point I'm plugging in. The other point is helping to get the direction. So we have from 2, 1, 3 towards 5, 3, negative 3. So we sit down and say, what's the vector? Look at the change. 2 to 5, up by 3. 1 to 3, up by 2. 3 to negative 3, down by 6, so negative 6. So that's the vector. Find the length. Find your unit vector by dividing by the length. Now you take your dot product, and if you've lived a good, clean algebra life, you should get one of the answers. In this case, it was 3. All right. Any questions? Cool. So now we get into the fun ones. Number 7. Find the second order Taylor polynomial of the function gst equals s squared t minus 2st cubed at the point 2, 1. Okay, well, I think we'll still ask this question. What kind of problem is this? Yeah, second order Taylor polynomial. How do we know it? Because they are very blunt. And they say, thou shalt do a second order Taylor polynomial. Now, why do we ask questions about second order Taylor polynomials? Sometimes we ask because we want you to do approximation. But oftentimes we ask to say, do you know how to take your partial derivatives? And do you know the formula? So let's just quickly remind ourselves of the formula. So g of st, well, your 0th layer is just the value of the function at the point ab. Then you go up to your first derivatives, gxab, x minus a, gyab, y minus b. Then comes the fun part, second order. So gxxab, that'll be part of it. What do you need to have attached to this? Don't forget the half, that's important. And x minus a squared. Then comes the next term, gxyab, which needs to have, yeah, it's a 1. So we don't need to write it. What else do you need? X minus a, y minus b. Then your last one, gyyyab. What goes in front? 1/2, good. And at the end? Y minus b squared. In some sense, you can figure it out, right? y, so I should have 2 y terms. Here's an xy, so I should have an x and a y. xx, so I should have 2 x terms. So the hardest thing about second order Taylor polynomials, after you remember the formula, is just writing stuff down. Lots and lots of writing here. Other than that, it's not so terrible. So I'll just show it, because this is what I got. So you take your function and you find lots of partial derivatives. After you find partial derivatives, you plug them in. Lots and lots of plugging in. Just take your time. Don't rush. And I see already that I messed up on the previous one, but that's all right. Okay, so I had x's and y's. These should be s's and t's. I got caught up. And yes?
Can we expect a second order Taylor polynomial on the exam tomorrow?
It's fair game.
Would there be any more than 2?
Like third order? That sounds cruel and unusual. No, we wouldn't do that. Now, let's talk about some things. So if they ask you in a long answer problem about second order Taylor polynomial, you just got to sit down and do the work. And I suggest don't expand unless you are told to. So in other words, leave it as your s minus t's and t minus 1s. Because that's actually the useful form. What if they give it to you as a multiple choice? Is there anything you can do then? So what's the punchline about Taylor polynomials? Taylor polynomials are designed so that the partial derivatives match the function. So if you don't want to go through all the work, just say, let me start just testing some partial derivatives of the answers that are, I have 5 answers. Just test some partial derivatives and say, this partial derivative doesn't match. OK, that's out. Doesn't work. Oh, this partial derivative doesn't match. That one's out. So you can go through elimination if you're like, I don't have the patience to go through and work it all out and do expansion. Now, how will you see it? Will you see it? You'll know in about, 28 hours? Yeah, 28 hours. So, any other questions on this one?
On the second order polynomial equation, you divide the x minus a squared over 2 instead of putting the 1/2 in front.
You can put the x minus a squared over 2. You can put 1/2 in front. As long as you remember, you have to have that half somehow. So there's lots of ways to do it. And once you start hitting third order, then you start getting all sorts of coefficients. You get 1/6, you get 1/2. All sorts of fun stuff can happen. All right. That brings us to number 8. This is a good one. Okay, so this used to be a quiz problem back in the day. And I feel sad that you didn't get to see it. So it's like, all right, we'll put it on the practice. So f of xy, it's a differentiable function. And now you can see the typo. It's just one function. I know, gasp. What? Okay. Which satisfies f of t cubed minus t plus 1, comma 2 minus t squared is t to the 4th minus 4t cubed plus 4t plus 6. And looking ahead, we're going to find the derivative of the right-hand side. We're going to use the chain rule to find this derivative. And then we're going to end up finding f sub x at 1, 1 and f sub y at 1, 1 by following what it tells us to do. Now, there is something about this problem that's kind of clear about what rule or what technique we need. What is this problem testing us on? Yes. How do we know? Because it tells us. Now, it won't always be so explicit. So how do you know when you're in a chain rule situation? What are you looking for? Lots of variables. Okay. So lots of variables, sure. But what else are you looking for? Sorry, well, f is a composite function. Okay, good. Composite function is another way of saying functions inside of function. So you might notice we have t cubed minus t plus 1 is a function. We're plugging into a function. 2 minus t squared is a function. We're plugging into the function. And so we're like, so this is, we're plugging functions into functions, chain rule. So even if it hadn't explicitly said chain rule, we would know chain rule is in play here. Okay, so let's quickly, this is saying find the derivative with respect to t of this expression. So let's draw the tree. I like the tree. What does f depend on? X and y. What does x depend on? T. And y? T. So you have your f sub x, x sub t. These are your derivatives, f sub y and y sub t. Now, of course, x sub t is just really the derivative of x with respect to t. Y sub t is the derivative of y with respect to t. So we can find these pretty quickly. I don't know if there's much else to say. Do we have answers? Does anybody know what fx at 1, 1 is? -4? Good. That's right. Fx at 1, 1 is -4. Fy at 1, 1 is -2. Now you might say, can we say anything else about the derivatives of f? And the answer is no. Literally, you can say nothing else about any derivative about f anywhere except at 1, 1. Because we don't know what f is. We're just seeing a little tiny bit of f. And so since we don't know what f is, we can't make any conclusions about derivatives. But it turns out, the reason that this all works is that if you were to think of this as a parametric curve in the plane, you're crossing through the same point, namely the point 1, 1 twice. So that's why it works. So let's see what happens. Part A, no surprises. You just take the derivative. Part B, you set up your tree. You find the chain rule, and you say, all right, well, I have f sub x times 3t squared minus 1, f sub y times minus 2t. And now you plug in t equals 1. And you get a relationship for fx11 and fy11. Plug in t equals -1, 1. Again, another relationship. And you fall into the classic 2 equations, 2 unknowns. We are pros at 2 equations, 2 unknowns. And so now you just combine them together, and you solve, and you get your values. And life is good. All right, any questions for this one?
Can you explain the parametric curve and it's like the 2 points or something?
Well, yeah, so you don't actually need to know why it's true. But what happens is that there's this point 1, 1. And what's happening is if you think of this as your x of t, y of t, as t varies, you're moving through the plane. And so there's like a loop. And so you're passing through the point twice. And what you're doing is you're basically comparing your 2 pass-throughs to extract information, is what's happening. So that's why it works. But you don't need to know why it works to get the problems, that get the correct answer. Other questions? Okay. We're doing great. Plenty of time. We'll finish. Number 9. Find and classify the critical points of the function 2x cubed minus 2x squared y plus 6xy plus y squared minus x squared. Now, these problems are very easy to spot. What words are you looking for? Find and classify critical points. They always say the exact same thing. So let's quickly remind ourselves of the classify and also of the find. How do you do the find? Gradient equals 0. So you set gradient equal to 0, which really says you take your partial derivatives equal to 0. We will never ask a find and classify problem for a function of 3 variables because you don't have the tools. Because you need to take linear algebra before you have the tools. And this is not a prerequisite. So it'll always be a function of 2 variables. So you have your 2 gradients, you set them equal to 0, 2 equations, 2 unknowns, but 2 interesting equations because they tend not to be simple. They tend to be polynomial. So that's your find. Now for classify, here's where things get spicy. You create a function composed of the second derivative at x, second derivative y, and the mixed partials squared. Then you plug in at your critical points, and you have a couple of possibilities. If this value is negative, what does that tell us? Saddle. Because what happens when being negative, it says in one direction you're going up, in a different direction you're going down, so you have that sort of mixed behavior. If we're positive, then we split again. And we look where? gxx or gyy, doesn't matter. So we say, okay, now look at gxx. Suppose that's negative. What are we? Max. And this gets back into our second derivative test from Calc 1. What happens if we're greater than 0? Well, yeah, it's the opposite, min. Now, if we end up getting 0, what do? We give up, correct. That is the correct thing. You just say inconclusive. That sounds like it's more cool than like I gave up. But we really are just giving up because we don't have the tools to make a decision at that point. All right, so how many critical points were there? 3.
Is it possible to like have inconclusive on a test? And should you just like write inconclusive?
If you get 0 on a test, just write inconclusive, and just say double check to make sure. But if it's inconclusive, you just say it's inconclusive, and I'm not going to go further. All right, so there are 3 critical points. How many maxes? 0. How many mins? 1. How many saddles? How many inconclusives? 0. All right. So, good. So you went through the find. You set up. Now, when you are going through and finding your critical points, there tends to be 2 things you want to look for. Factoring, substitutions. Factoring is ideal, but it won't always happen. Substitutions, you say, one of the equations, I have just one of the variables showing up once. So for example here, g sub y, there's only a single y. That lets us say, okay, I can replace y by x squared minus 3x in the other relationship, which gets us down to 1 equation, 1 unknown. And then you just carefully work through it. Chip away, be patient. So it's easy to make copy mistakes and little multiplying mistakes. Use parentheses. Pay attention to expansion. Small things lead to big changes. So it's not worth it to rush. Take your time. The difference between people who do well and the people who struggle is a lot smaller than most people think. It just comes down to being careful. Learn to, as the great philosophers have said, check yourself before you wreck yourself. So keep that in mind. All right, so anyways, we ended up with 3 values for x. We know y depends on x. So we say x equals 0, y equals 0, x equals 1, y equals minus 2, x equals 5, y equals 10. Go through and find your second order derivatives, plug it in, pay attention to your signs, do your classification. All right, so that leaves us with our final problem. Okay, so for xy greater than or equal to 0, use the method of Lagrange multipliers to find the minimal value of 2x plus 3y plus xy, given that 2xy equals 21 plus 3x. What technique should we use? Yes! It gives it away. Now, if you're told to use the method of Lagrange multipliers and you don't use the method of Lagrange multipliers, what happens? You get few, if any, points. So, pro tip, follow instructions. If they tell you to do something, do it. If they tell you not to do something, don't do it. It's the secret code, but it turns out to work really well. Now, suppose maybe they don't tell you method of Lagrange multipliers. How do you recognize it? What are you looking for Lagrange multipliers? You're looking for a constraint. So you should have 2 functions. One that you're trying to make big or small, and we won't be coy, we'll be very explicit. And then one that has a constraint. Now, is there anything suspicious about our constraint? I'll point out the constraint will have the equal sign. Is there anything bad here? Or maybe I shouldn't say bad. Not good. Yeah, we want your constraint should look like g of xy equals c. So how do you fix it? Yeah. It's the power of subtraction. And now you're ready to go. All right, so we now know the technique. Lagrange multipliers comes down to setting up a set of equations. Where does it come from? Gradient of f equals lambda gradient g. When in doubt, solve for lambda. Now the idea, what's the answer? So let's make sure another thing is make sure you know what they're asking you to find. Here, this is saying find the minimal value. So what is the smallest value that we can extract? What's the number? Does anybody work this out? No? 36. So make sure there's another condition here that you're at x and y are both greater than or equal to 0. Okay, so you have to be careful here. All right, so what happens? We set up gradient of f equals lambda gradient g. The whole punchline is we say the constraint gives us the relationship. The gradient of f equals lambda gradient of g, when we work it out, gives us another relationship. Now you have two relationships, which lets you solve for a point. In this case, you only get one. If you only get one, that's your point. We're not going to be coy. Lagrange multipliers does not have a built-in, this is a max, this is a min. You just say, if I've got 1 point out, that's my point, plug it in. If I got 3 points out, and I have to find which one's the min, what do? Test them all. And just say, whichever one's the smallest, that's my answer. And then you're done. All right, that's our time.